All right, it's rolling. Here we go. So, guys, again, like we said before, as we start this new stuff, it's the beginning. So, anytime something is the beginning, try to. It's motivating, right? It's the beginning. So you can say, "Hey, I'm going to focus from the beginning. I'm not going to get behind," and that allows me to stay up to date because this is chemistry. If you get behind in chemistry, it's like math. It'll be really tough. All right, so this, you have one of these in your notes, but I'm going to give you another one. We're going to label this thing. We're going to color it. It's a tool, right? If I give you, like we said before, if I give you a router and I say, build me a picture frame, is that going to do y'all any good? If you used woodworking tools before, it'll do you some good, right? But if you've never used tools before, and I didn't teach you anything about how to use a router, you might use it just, it's kind of like trying to make a monkey use a computer. It's like, it's just going to be use it to bash something, okay? It's not going to work real good. Same thing with a periodic table. If I don't teach you how to use the periodic table, you may think this is easy. It's like, you're going to let me use a periodic table on a test? I'm like, yeah, I am going to let you use a periodic table on a test. But you got to know how to use it, right? If I say, how many protons are in lithium, and it just says Li3, and then some number at the bottom of it, if you don't know what those numbers mean, it's of no use to you. Might make a good guess, but it's of no use. So we got to know how to use this thing. This thing has unbelievable utility if you know how to use it in terms of chemistry. Right? This tells you so much about ultimately we want to learn about the reactivity, how elements react with one another. Because what you're going to find out is this table has all the stuff we know about the universe on it. Like, it's really cool. It's like you could ask yourself, is there any place that you could go find everything there is in the universe? Yeah, there is. It's right here. Fundamentally, there's this. Everything there is in the universe that we know about, maybe there's other stuff, but everything that we know about, even some things that we make in the lab. There's places around the world where we take like really tiny stuff and then make it go really fast and slam them into each other, like basically like close to the speed of light. Accelerate two little tiny particles super, super fast in opposite directions and let them go wham, and then see what happens. And crazy stuff happens. And you actually end up creating stuff that's, well, this table is a little bit old, so it's not even, there's more stuff and so we create them in a lab, and then immediately they usually decay into other stuff. But anyway, there might be other stuff out there too. We don't technically know. Okay, but that's pretty much all of it that we know about. Okay, we'll do a lot more with that. So, what is the atom? The atom is the smallest particle of an element that still has the properties of that element. So, I'm going to do that. Remind me in just a minute. We'll do that. I'll do it in just a minute. Okay, so you have to understand the atom. So the fundamental unit of matter is the atom. And we've had this for a long time in school, so we're not going to belabor the point too much. But the nucleus is the center, right? The nucleus is the center of an atom. And the nucleus is made of things called protons and neutrons. If you're pro something, are you positive or negative it? If you're pro this, that means you're positive. Yeah, you want it to happen, right? You're pro blank. You like it. Well, what's the charge of a proton then? Positive, yes, and we know that stuff, so positive. Neutron. If you're neutral something, are you either way? So a neutron has no charge. It's no charge. And then, well, what's left? You got positive, you got no, and you got electrons, which is negative. Okay, electrons are negative, and so does electron necessarily mean negative? No, but when you think electricity, I think of the movement of negative charge. We talked about that. Like, that's what's flowing. So electrons are negative. So we're going to learn a lot more about the actual structure of this thing. But in the center, like we said, are the protons and neutrons. And they're way bigger. Did y'all know that? Did you know that protons and neutrons are like 1,835 to be exact, I think. 1,835 times more massive than an electron. So these things in here, it's like saying, I don't even know a good analogy. It'd probably be like an elephant compared to a mouse, sort of. Something like that. That's how the difference. So these things in here, even though we're talking about things that are unimaginably small, the nucleus is way more massive, okay, than the electron. Okay, the electron is much smaller, 1,800 times smaller. So that's a pretty big difference when you're talking about things that are already really little, like crazy little. Okay, okay, so you got nucleus, electrons, and this is not correct totally, right? We'll learn more about this as we go through the history, but electrons go around the outside of an atom more like bees buzzing around a hive. When you you can't ever pinpoint the location of an electron, but you can say, okay, this electron's in this area. And we have a cloud, really. It's more like a cloud of negative charge rather than a point. So you can't say that point's negative. In a real atom, it's more like this is the cloud of negativity, basically. Okay. All right, so remember some basic things. The element is the simplest form of matter, so all the things on the ceilings are elements. And we define the element like we said before. This over here, AU is gold. Y'all see that right there? I see that 79 right there? That's gold. Everybody knows gold. It's a valuable element. Well, look what happens if that 79 changes to an 80. Gold becomes, you know what the symbol Hg stands for? Anybody? It's mercury. Good. Yes, sir. Nice, man. It stands for mercury. It stands for mercury. All we have to do, guys, is add one proton to the nucleus. Gold is now mercury. It is no longer gold anymore. Okay, and we'll learn a lot more about that. You can take an electron away from gold, and it's still gold. You can even change the amount of neutrons, and it's still gold. But if you change the number of protons, it's no longer the same thing. So the number of protons is the identity of the element. It's its definition. Okay. All right. So water. This is some terminology. It says water, H2O, is made of 2 atoms of the element hydrogen and 1 atom of the element oxygen. So sometimes we don't use terminology correct. So you could say something like this. Would this be a correct statement? I have 1 atom of water. Is that a correct statement? No, it's not a correct statement. Okay, because is this a correct statement? Water is made of 3 atoms. Is that a correct statement? Yes, that's a correct statement, absolutely. We could say that water is made of 2 atoms of hydrogen and 1 atom of oxygen. Those are all correct statements. The way you would talk about the thing in itself is call it a molecule. Okay, it's 1 water molecule. So molecules are made of atoms that are covalently bonded together, and we'll get to that more. Okay, all right. So, guys, we need to understand our history because history gives us perspective. So as we go through some of this stuff, we're going to go through this part quickly. We've already got this written down. I think we already got this part written down for the most part. Okay, so we can go through pretty quickly. On a test, what are you responsible for? You just need to know the basics of what they did. Democritus. Democritus, a long, long time ago, 400 BC, before Christ. We're way back. First to name the atom. They didn't know anything about subatomic particles, guys. Nothing about that. I mean, this is way long time ago, okay? But this guy was the first person. Maybe other people did it before him, but they didn't write it down, right? Somebody in ancient Mesopotamia may have said that, hey, I think things are made of solid, indivisible things. But nobody wrote it down. But Democritus did. And he named it atomos, which is Greek for indivisible. So it means that this something, if you take something and continue to cut it, eventually you'll get to a point where you can no longer cut that thing or it's not the same thing anymore. It's indivisible. Okay, so he called it atomos, which we call atom. Democritus named the atom. 1803, fast forward a really long time, like 2,200 years. John Dalton said the atom is a solid sphere that can't get any smaller. Guys, that's really similar to this. It's kind of almost the same. You know, it's just basically, he said, okay, it's a solid sphere. They can't get any smaller. That was the idea in 1803 from John Dalton. He also added this. Elements are made of atoms that all have the same mass. Okay? So elements are made of atoms that all have the same mass. And compounds are atoms of different elements combined. Okay? 1869, we get the first periodic table. Where do you think this guy's from? Russia. Yeah, Dmitri, right? Dmitri Mendeleev. I like the name Dmitri. Dmitri. He developed the first periodic table. Now, guys, if we look at the periodic table on the ceiling, look at the numbers. Or, well, this may not be because it's not in order on the ceiling, but look over here. Do you see how the periodic table, it goes 22, 23, 24, 25, 26, 27? If you'll notice, it does that the whole way down here. It's like 118 is where it ends. I think this one doesn't, but the newest ones do, I believe. That one's not organized based off atomic mass. That one's organized based on atomic number, the number of protons. But in 1869, Mendeleev organized it based off of this bottom number down here, their atomic mass. Okay, so he organized it based off something different. It changed over time, but that's all you got to know. So for understanding, learning purposes, for a test, name the atom, solid sphere model, first periodic table.
Has the human eye ever seen an atom?
Good question. So, not without unbelievable assistance from the best imaging tools that humans have made. So remember, on the head of a pen, you can fit like 1 million carbon atoms, across it. It's insane, right? And so if you were to take the head of a pen, you can fit 1 million carbon atoms from like one end to the other. That's insane, right? So can you actually see it with your eye? Not even close, right? It's not even remotely close. But if you can indirectly see them using imaging tools. I think I need to look it up, but maybe with like the best electron microscopes, I think we've taken some pictures of like carbon atoms, but it's not really, it's hard to say it's like a picture of an atom, but it's a picture of a bunch of them. And you could kind of see them like next to each other in the little kind of lattice that they form, that carbon atoms form when they're next to each other. So it's not particularly like, hey, we've taken a picture of a single atom. But the way we know, it's good, like, how the heck do you know that this is true? Right? A lot of it is like indirect experimentation. We know this, if this happens, this must be true. Not that we can actually like look at it and say like, hey, you got red hair, because I can observe it. It's more like indirect observation, like, hey, we do certain experiments that tell us the only way this can be true is if you had red hair. So that's kind of most how we get the information about atoms. You can't really see them. But maybe one day, I don't know, maybe as technology continues to improve, and who knows. All right, we keep going, guys. Look here, we jumped all the way from the beginning of the 1800s, 1803, 100 years later, to J.J. Thomson and this plum pudding model. All right, y'all ever seen plum pudding? Anybody ever eaten plum pudding? I haven't, but I assume it must look something like this, with like plums and Jell-O. You know what I'm talking about? Okay, I don't know. I think of like what's the stuff you get on Christmas sometimes? Fruit cake. Yeah, something like that. Yeah. I don't know. So it's like something like that, where you have J.J. Thomson said, okay, my model of the atom based on experimentation is this. Picture like a big thing of Jell-O that's positively charged. Okay? So you got this positively charged sphere with little negatively charged plums in it. Does that kind of make sense? That's his model of the atom. We know that's not correct, but again, they didn't know. They're just building on knowledge, trying to expand on what we know and understand about the atom through experiments, indirect observation. So J.J. Thomson, plum pudding model, positively charged sphere, negatively charged things in the sphere, or think of Jell-O with plums in it. Okay? Then you go to Ernest Rutherford. This one is the big one. I bet you've actually heard of this before, even before this class. Have y'all heard of Ernest Rutherford? I think he did it in middle school. His Goldfull experiment. Coach Runge talked about it. We've talked about it before, me and him. So this is crazy, guys. This is what he did. So Goldfull experiment, he determined that the mass of an atom and its positively charged particles were in the nucleus, with the low mass, negatively charged particles surrounding it. Okay. So picture this for a second. So let's draw it. just for a split second so you can kind of, it's good to visualize this stuff. To me, if I can visualize something, I can understand it and I can remember it. All right. So this is the best drawing I can do. So picture like a alpha particle gun. All right. So we've got this gun right here that's shooting out alpha particles. All right. And here, picture a super thin sheet of gold. Like just, like aluminum foil, like you put on stuff. Picture that, but gold. Like made out of pure gold. Okay? Expensive aluminum foil. And then around the outside of it, you have detectors that can detect the presence of really small things. Okay, just picture that. Like it knows if one of these alpha particles, if it bounces off that gold foil, it can detect it and where it bounced off. Okay? Well, what do you think happened? What do you think? Do you think when he shot the alpha particles at the gold foil, do you think they just went straight through it? Do you think they bounced off? What do you think happened?
Straight through.
Okay. Anybody else? Bounced off. Okay. Well, just to keep it simple, let's say that about approximately, I don't know if this number is exactly right, but it's close to this. 99.9% of the time, almost always, they went straight through the sheet of gold, like it was not even there. Went straight through. So almost always they were hitting right here. You were getting a lot of detection of alpha particles right here, all the time. And so, but every now and then, one would bounce off, and you'd get one there. One there. And he's like, what the heck? It's like the thing's not even there. It's just going straight through it. So he's led to a conclusion. He said that, first off, the mass of an atom must be in this unimaginably dense center called the nucleus. So this is the nucleus, right? And this is where the protons and neutrons are. And that the other things, the negative charge, must be on the outside, out here. And think about this for a second. Is that actually he could conclude, because think about it, everything just went straight through over time, so it was literally hitting nothing. And we know this to be true today, that all stuff in the universe is mostly just empty space, including you and me. That's a crazy thing to think about. But if you were the size of an atom, like say you were a proton or neutron, like you could make yourself that size. You could shrink down to that size. You would pretty much see nothing else. It would just be literal nothingness, because when you get down to the size of a nucleus of an atom, the electrons, again, are like, it's like you got a nucleus and the electrons are kind of buzzing around the outside, and they're really if you're the size of a nucleus, they're way far away from you. You could be like, it'd be maybe like a football field away. If you were to scale up the nucleus, trying to make this make sense. If you were to scale up the nucleus, there's a good YouTube video about this. If you were to scale up the nucleus like the size of a blueberry, the next closest subatomic particle would be like a football. I need to look at. We'll watch it like a football field away. Okay, it's way crazy. So even a solid, like this solid table, is in reality. Well, not in reality, because this is our reality, but in a quantum reality, like quantum mechanical stuff, like subatomic stuff, like below even the size of an atom, is mostly just emptiness. It's like nothing, like space, nothing. It's pretty crazy. Okay? All right. So anyway, this was Rutherford's experiment. Does that blow anybody's mind? It blows my mind. It's crazy. Okay? I think if we watch the video, it's way better description than what I just did. We'll watch it. This experiment led to a much better model of the atom. And if you know anything about the atom, before this is getting way closer to what we know to be true, right? Like this was a big leap, guys. This put the positive charge in the middle, which is what is right, and the negative charge on the outside. Before it was not like that. It was kind of flipped. You had like a positively charged Jello mold with negative charges all throughout it. Okay? Now this got us more where you got a dense center, which is what we know to be true, and negative charge on the outside. Okay? Okay? All right, guys, last three here. We've got Henry Moseley, Niels Bohr, and Schrodinger and Heisenberg. Hey, there's Erwin Schrodinger right over there. Destiny drew that. She's amazing. She did that with a Sharpie. What the heck? Talented people, man. That's cool. So Henry Moseley discovered the number of protons is unique to each element. This guy's changed the way the periodic table is arranged. Okay? Henry Moseley changed the periodic table to be arranged based on protons, not, which is atomic number, not atomic mass. And we hadn't even talked about atomic mass. Mass is how much stuff makes you up, right? Well, atomic mass is basically how much stuff makes up an atom. So what's the stuff that makes up an atom? Think about this for a second. What's the stuff that makes up an atom? We say again, just like we said at the beginning of class, it's and neutrons. Okay. So remember what I said? A proton and a neutron are basically the same size, the same mass. So they're way bigger. They're 1,800 times bigger than an electron. So when you do atomic masses for elements, guys, see it's like 55.845 right there. You don't take into consideration the mass of the electron. They just basically say, hey, the electron's so tiny, we're just not even going to worry about it in terms of atomic mass. We're just going to worry about the stuff in the nucleus, protons and neutrons. And we'll take that mass into consideration, okay? Because protons and neutrons, I think a neutron's just actually a little bit bigger than a proton for whatever reason. I don't really know. But they're almost the same. They're almost the same. Okay, so the atomic mass is the number of protons and neutrons. We'll get way more into that. Okay. Guys, we'll still do this one in class today. Y'all have heard of a Bohr model. Has anybody ever made a Bohr model before? If you notice this is what this Bohr model is. Like I said, it was such a big deal. It's still used today, over 100 years later, to describe the structure of an atom, right? Even though it was not entirely correct in terms of how electrons move. So Bohr said that electrons move in fixed orbits around the nucleus, right? So electrons would move. What do you know? What moves in fixed orbits that you know about? What could you think of that would maybe? What would be analogous? If you could think of an analogy to describe this model. Yes, very good. Exactly. Am I nice? Earth to the sun, whereas the center would be like the sun, the nucleus, and that Earth would be like the electrons. That's a great analogy, and it's truthfully, it's a great way to think about an atom. It's a great model to use, even though it's not entirely correct. It's still a good model, okay? And that's what this model says: is that electrons move in fixed orbits, just like the Earth moves in a fixed orbit around the sun. Because we can predict where the Earth's going to be around the sun. We do it all the time for seasons and things like that. Okay, so that was Bohr model. Electrons are negative particles that travel in fixed orbits of a positively charged nucleus that is made of positive protons and neutral neutrons. And then we had this one, guys, Schrodinger and Heisenberg, the electron cloud model. So to be clear, like we said, this is not correct. Electrons do not move in fixed orbits. Okay? They move more like bees buzzing around a hive. So electrons move in things called orbitals. Okay, they move in areas. Okay, so we know we can define an area that an electron moves in. Okay, so the electron's most likely to be found in this area. And what you call that, when we get into it in more detail later on, is it's called an orbital. So it's not an orbit, it's called an orbital. And we'll get into the orbitals. So that's what these guys said, is this: if you think of a beehive and the bees buzzing around it, it just looks crazy, right? It's just more like a cloud of bees. And that's the way you want to think of this, is the electrons make like a cloud of negativity. And guys, these things are moving unbelievably fast, like approaching the speed of light, okay? So if something's moving unbelievably fast, it basically disappears, right? Think about that. If you were to like, eventually if you can see this, you can do it, I don't know, if we had something we could spin around really fast, like you know how you take something and spin it like this? When you start to spin it slowly, you can watch it, right? Oh, you ever try to do this? You ever watched a fan and try to look up at the fan and try to isolate a blade with your eyes? Okay, so if the fan's moving rather slowly, say, but it kind of looks like a blur at first, if you'll kind of really focus your eyes, you can follow one blade. Like you can see the blade, right? You can be like, oh wow, now I can see one blade. You see what I mean? But if you get that fan going unbelievably fast, eventually the blades will just basically disappear. Right? Because they're going so fast. And you can never know where a blade is at a given time. It's just because it's going too fast. And they're moving, and the blade's not moving randomly, but the electron is kind of moving randomly in an area. So that's why we have this cloud model. So it's an electron cloud model, and the cloud is negatively charged. The center is positive. Okay? Okay, man, some cool stuff. They do not travel in fixed orbits. The nucleus is surrounded by an electron cloud that is divided into shells, and we'll talk about the shells. But electrons do not travel in fixed orbits. So that was the Schrodinger and Heisenberg electron cloud model and their uncertainty principle. Okay, all right, group. So this part here is just for you to kind of take a few notes on this, to write a few things down if you haven't. Because again, this is, so I'm going to let you guys write a few things down here if you want. To have this as part of your notes, because we will have a quiz tomorrow. So the nucleus, again, this is stuff, all this we've already said. But if you want to write down just some bullets, the nucleus is unbelievably dense. Y'all understand? This is crazy. We might have said this before. Does anybody remember how dense the nucleus is? And a description. Remember what we said? Did we say that? Talk about how dense the nucleus of an atom is? Okay, picture this for me while you're writing that stuff down. If I have a 1 by 1 by 1 foot box, okay? So about the size of like, well, y'all get the point what I'm talking about? Like a box like this big. Here we go. 1 by 1 by 1. Length, width, and height. Box. That big. Yes, ma'am? Can you take attendance? Yes, ma'am. Dang it. Hang on. Let's take attendance real quick then. Brief interlude. So we can, I know I was going to do it, but let me just freeze it. My bad. Here you go. So if we have a 1 by 1 by 1 foot box, if you took basically all the cars on planet Earth, okay, all the vehicles on planet Earth, and put them in that 1 by 1 foot box, mashed them in there. So that even putting one car in a box that big doesn't even make sense, right? Y'all got what I'm saying there? And if you put all the about 6.5 billion, okay, put them in there, that would be about the density of a nucleus of an atom. I know it doesn't even really make sense. If you had something that dense, guys, and you were like, say you were like you had like godlike powers and you could hold it. If you dropped it, it would like go through the earth. It would like go through the center of the earth and go to the middle. It would just rip through the ground. It would be so heavy and dense. But that's the density of the nucleus of an atom. So you can imagine, it's like, how is this thing so densely packed together? Well, that's, and it's so cool. Think of something being that dense and that packed together. But and we'll talk more about that, the kind of forces that hold the nucleus together. Because that should lead you to think about something else. What's the charge of the nucleus? Positive. So how in the world if we said the nucleus is that dense, well, that means you're stuffing positive charges unimaginably close together. And what do you know about positive charges? They like to be beside each other? No. They want to break apart, right? They want to get away from each other. They don't want to be super close together, okay? And so that leads to a great thought. It's like, well, how does that stay together then? Why don't all nuclei just fly apart like crazy? Well, there's forces that hold them together. Fundamental forces of the universe, just like the law of gravity, but relative to subatomic scales. Okay, so we've got Sydney. There's a lot of people missing. Glad we did this. Rayleigh, Riley, Austin, Emma, Lucas, Madeline, Nathan, Aubrey, Kyler. Or Nathan, Aubrey, Kyler here. Brennan. Probably good. Okay. All right. Good guess. Okay, but that's just a little bit, some side notes about density. Again, we'll talk about that more. Just subatomic stuff it always just blows your mind because it's so like something we don't understand, right? And can't experience. And so it makes sense that we really can't appreciate it because you guys know it's so hard to appreciate something you don't fully experience. It's very hard. Very hard. And so nobody's experienced this, so it's hard to appreciate it. Okay, so we're almost done, guys. This as a matter of fact, this is the last one. So we look through here and we'll stop. Dense center, made of protons and neutrons, positively charged. We're talking about the nucleus, and it's where the mass is located. The atomic mass is based off of the nucleus. The electron cloud is the space around the nucleus. It's broken down into shells or energy levels, which we'll talk about. The electrons in shells further from the nucleus have the most energy, and that should make sense. We'll talk about why. The electrons in the outermost energy level are called valence electrons. Guys, this word right here is going to be really important. Valence electrons, we're going to talk about that a lot because those are the electrons that do the bonding. Okay? And bonding is what chemistry is about. Okay? Negatively charged, and it's where the volume of the atom is located. Okay? All right. Cool. So that's it. We'll stop there. Anything? Okay. Very good, guys. Very good. Stop there and start back up tomorrow.